So let us get started with linear algebra, unit 1, vector spaces, LAQ. So the first important question is define null space and find spanning set for the null space of given matrix. And a matrix is given. It is 3 by 5 matrix. So first let us define what is null space. So null space of an m by n matrix A is the set of all solutions to the homogeneous equation Ax is equal to O, and it is represented in set notation form as null A is equal to x such that x is in R power n and Ax is equal to 0. So first let us write the given matrix. Given matrix is A is equal to -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4. Now we will write the augmented matrix. What is the augmented matrix? A 0 is represented as, we need to copy this A matrix, -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4. And one more column we need to add, which contains all zeros. Now we need to make these two zeros. So what row transformation should I apply? We need to use R1 to change R2 and R3. So R2 is 3R2 plus R1. R3 is 3R3 plus 2R1. So what do you get? You will get first row we are not changing. Now second row, 1 into 3 is 3. 3 minus 3 is 0. Then -2 into 3 is 6. 6 minus 6 is 0. Then 2 into 3 is 6. 6 plus 1 is 7. Then 3 into 3 is 9. 9 plus 1 is 10. Now 1 minute, let me do this one again. So this is 2 into 3 is 2 into 3 is 6. 6 minus 1 is 5. Then over here -1 into 3 is 3. 3 minus 7 is -1 into 3 is -3. -3 minus 7 is -10. 0 into 3 is 0. 0 plus 0 is 0. Now R3, what we are doing? 3R3 plus 2R1. So 2 into 3 is 6. 2 into 3 is 6. And -3 into 2 is 6. -6. 6 minus 6 will become 0. Now -4 into 3 is -12. 6 into 2 is 12. 12 minus 12 is 0. Now 5 into 3 is 15 plus 2R1. So -1 into 2 is -2. This is 13. Next, 8 into 3 is 24. And 1 into 2 is 2. 24 plus 2 is 26. Then minus 4 into 3 is minus 12. Minus 7 into 2 is minus 14. That is minus 26. And this will be 0. You understood how I applied the row transformations? Now, you can see in the second row, we can take 5 common. In the third row, we can take 13 common. So, R2 is R2 by 5. R3 is R3 by 13. So, we will get minus 3, 6, minus 1, 1, minus 7, 0, 0, 0, 1, 2, minus 2, 0, 0, 0, 1, 2, minus 2, 0. So you can see two rows are identical. So we can subtract them. R3 is R3 minus R2 we will do. So first row remains the same, second row remains the same. Minus 3, 6, minus 1, 1, minus 7, 0, 0, 0, 1, 2, minus 2, 0. Now the whole third row will become 0. Now R1 is R1. Now what will I do over here? R1 is R1 minus R2 by 3. Okay. Why? Because I want to make this 0. So that is 1 minus 2, 0. Minus 1, 3, 0. Then second and third we are not disturbing. So what did we do over here? We first divided R2 by 3 and then we subtracted it from R1. Okay, so what is the general solution now? The general solution is x1. From the first row, you see how I am taking. First number, multiply with x1. Second number, multiply with x2. Third number is 0, so x3 will not come. Then minus x4 plus 3x5 is equal to 0. Now from the second row, you can see x3 plus 2x4 minus 2x5 is equal to 0. And in the third row, 0 is equal to 0. So from the first equation, I will find x1. x1 is 2x2 plus x4 minus 3x5. This is equation number 1. Then x3 is minus 2x4 plus 2x5. This is equation number 2. Now you can see x2, x4 and x5 are on the right hand side of equation number 1. So these are free variables. Free variables means those are independent variables because x1 is dependent on these three. So the general solution, how can we write? The general solution can be written as linear combination of vector with free variable. So how can we write? x1, x2, x3, x4, x5. That is equal to, we can write x1, how can we write? 2x2 plus x4 minus 3x5. x2 as it is. x3 is minus 2x4 plus 2x5. x4 as it is, x5 as it is. So this we can separate now. x2 we are taking common. So we will get 2, 1, 0, 0, 0. Plus x4 if we take common. 1, 0, minus 2, 1, 0. Then if we take x5 common, we will get minus 3, 0, 2, 0, 1. So that is equal to x2 into this matrix we write U plus x4 into V plus x5 into W. So finally what can we say? since every linear combination of UVW is an element of null A, therefore, in flower brackets, you write UVW is spanning set for null A. Understood? Now let us take the next LAQ. If a vector space V has a basis beta equals to B1, B2, so on up to Bn, then show that any set in V containing more than n vectors must be linearly dependent. So first let us see what is given to us. So given that V is a vector space. And what is the basis given? Basis beta is equal to B1, B2, so on up to Bn. Let U1, U2, so on up to UK be a set in V containing more than n vectors. Here the last element is K, which means K is greater than n. That is, K is greater than n. Now since K is greater than n, then we can write the K coordinate vectors. K coordinate vectors, that is U1 beta, U2 beta, so on up to UK beta, because beta is a basis, are in R power n. That is the vectors U1 beta, U2 beta, so on up to UK beta are linearly dependent. Therefore, there exist scalars C1, C2, so on up to Ck, not all zero, such that C1 into U1 beta plus C2 into U2 beta plus so on up to Ck into UK beta is equal to 0. Okay, this is the condition taken whenever elements are linearly dependent. Now let us see, since the coordinate mapping x tends to x beta is an isomorphism. What does that mean? That is 1-1 linear transformation from V with a basis of n, with a basis of n vectors onto R power n. That means C1 U1 plus C2 U2 plus 1 up to Ck UK of beta is equal to 0. Why? Since x tends to x beta is linear. That means C1 U1 plus C2 U2 plus 1 up to Ck UK is 0. Why? Since x tends to x beta is 1-1. So with at least one Ci which is not equal to 0, where I takes values 1, 2, so on up to k. Therefore, you can say that the set u1, u2, so on up to uk is linearly dependent.